Okay, so chapter 5 is oxidation reduction reactions. We call it redox. And it's oxidation reduction. I always thought it should be oxre, but that's not what they call it. So as in all chapters, you'll see the homework listed and we have the definitions. These are the vocabulary words that I expect you already know as we head into this discussion. And just glancing at the first two rows that I can see, I don't see a lot of this filled in. So oxidation reduction chemistry is electron transfer reactions. The electrons are actually moving around in redox. And there's different kinds of redox chemistry. In your introductory chemistry, you should have talked about different types of reactions. You would have introduced double replacement, which we've reviewed already, single replacement, combustion, combination, decomposition. Does that sound familiar? You talked about them in classes of reactions. Now we're going to look at them a little differently. Redox is electrons moving, and several of those types of reactions you looked at in intro are actually redox reactions. So things like single replacement is redox, combustion is redox, and combination and some decomposition is redox, not all. So redox chemistry can be defined in terms of oxidation and reduction. Does anybody know what oxidation is? It's not the gaining, it's actually the loss, right? You had it backwards. So oxidation is loss of electrons. And what's reduction? Gaining, right? Gain of electrons. And there's another way to define it also in terms of oxidation number. What is that? Anybody know? Because to me this always seems backwards. If you're oxidizing and you're losing something, but reduction doesn't seem to me like it should be a gain. That's why I used to get it backwards too, right? So the other way to think of this is an increase in oxidation number, and this one is a decrease in oxidation number. So as you're trying to remember that, because the loss and gain seems backwards to me, I brought my friend Leo. Leo the lion. For those of you watching the video. Hi. Okay. So, sorry. When I hang out with Leo, we talk. Leo doesn't have much to say. But when I talk to him, how's it going, Leo? He only says one thing. Grr. So, that helps me remember. Leo says grr. Loss of electrons is oxidation. Gain of electrons is reduction. That's my friend Leo helping us learn chemistry. So as you are transferring these electrons around, when something is oxidized, it's losing electrons. And we know about oxidation in everyday life. You ever see anything rust? Okay? You're oxidizing the iron. Have you ever opened a brand new thing of aluminum foil? Maybe you bought them on sale and it's been sitting in the cupboard for a while before you went to use it. And when you open it, it doesn't seem quite so shiny. And it sometimes you even can take your finger and run it across there and some white powder will rub off. That's aluminum oxide. So those things have oxidized. When pennies tarnish, that's oxidation. That's copper oxide, the dark brown coating on the penny that's no longer shiny. When your silver gets tarnished, that's silver oxide is forming, which is why you should not polish your silver too often, in my opinion. Every time you polish your silver, you're dissolving that silver oxide and you're actually removing a tiny bit of silver from it. When I started high school chemistry, I learned about that. And my mom had all kinds of silver, and it sat around the house getting oxidized. And part of our job as the kid was to polish that silver every week. I hated polishing silver. Every Saturday morning, we had to polish the silver so it looked nice and get any fingerprints off it from the week. And when I took chemistry, I went home and said, we shouldn't polish the silver anymore because we're actually throwing out some of the silver, so I'm not going to polish it anymore. Well, I'll tell you, my mother had a different idea than I did. I continued to polish the silver, even though I knew she was throwing her money down the drain, dissolving a little bit of silver. I now have the silver, and I treat it reverently, and I don't polish it regularly because I know it's not good for it. I polish it twice a year when I use it. I polish it before Christmas so it looks lovely, and I polish it again at Easter. And if I'm having a baby shower or something, I polish it then, right? But otherwise, I just keep it hidden so nobody sees that it's tarnished. That works better for me. Okay, so that's oxidation reduction. You see that. Also, have you ever looked at a bottle of chlorine bleach and read the warning on there and it says danger oxidizer? Have you ever seen that on there? Most people don't pay attention. Chlorine bleach is an oxidizer. It will do violent things. That's why it gets the bleach or gets the stains out of your clothing, because it is oxidizing the material that is causing the stain, and in doing so, it breaks it up and then it leaves the fabric. That's why chlorine bleach works. You have to be really careful. You should not have it sitting next to your hot water heater, because if it ever leaks and gets in there, the chlorine bleach will actually help add oxygen and it will make a fire go bigger. So you have to be really careful of that. Okay, so those are kind of the definitions. Now, the last definition that you really need to understand before you can be successful in this chapter is the one on oxidation number. Oxidation number is an apparent charge. So if you don't have these filled in, you're going to want to go back and fill in the rest before we move along. The apparent charge, it's not real, and it's an apparent charge that something would have if its electrons were transferred completely. So when things have been in a bonding situation, we always get the idea that when you have a covalent bond that you're sharing and sharing alike. But that's not what happens. Sometimes you have one element that's hogging the electrons because it's more electronegative. So you have these apparent uneven charges. Okay, my sister and I shared a car. She was a year older than me, and she had the car all the time. She just got in and left with it. Then we were sharing it, but it appeared to me that she had the car, which she did because she was out driving around in it, right? But it was still half mine. Does that kind of make sense? So somebody can be hogging the electrons, but they have not completely transferred. They hadn't transferred ownership of the vehicle to my sister. We were still sharing it. I just didn't get to drive very often. So we can assign oxidation numbers by going through some steps and looking at the formula for a compound. Now, the rules I'm going to go through are a little bit different than what's in the book. The other ones work too, but mine are better because if you follow these rules in the order in which they are listed, you will have fewer problems with hierarchy. You must follow these rules in the order in which they're listed, and the ones at the top go into play first, and then you assign as you go down. And if you get down here and this rule contradicts something that's up there, that's okay. You just go with what was up here first. So here's the rules. Free elements in their natural states have an oxidation number of 0 because it appears they have the same number of electrons they had when they were an element in their natural state. There's no difference. Monoatomic ions, when we've transferred electrons from or to an atom, they have an oxidation number equal to the charge. It appears that there is a charge because there is a charge, a real charge. So it appears that there is one. The sum of all oxidation numbers has to equal the charge on the species. If the species has no charge, if it's a neutral compound, then there should be no charge when you add up everything. But if there is a charge, if it's a polyatomic ion, then they will add to the charge on the ion. Now, how do you assign individual? Well, fluorine is the most electronegative element, so it has an oxidation number of -1 always. Next is hydrogen. It generally has +1 unless it's a metal hydride and then it's a -1. That's something where you have like magnesium hydride, MgH2. The hydrogen is the anion instead of the cation. Remember we said hydrogen can act like a halogen sometimes? Oxygen is -2 unless it's a peroxide. How do you recognize a peroxide? Well, you know the peroxide ion, O2, 2-, and peroxides, if you look at the Lewis structure, which you were exposed to a little bit in your introductory chemistry, it has 2 oxygens with a single bond between them. That's what makes it a peroxide. So now let's see what this means in terms of an example.